Okay, so we're going to talk about the this Bohr model. And what this is this is Bohr's model of the hydrogen atom. Now, what this means is we're saying it's Bohr's model of the hydrogen atom as if we were talking about one electron moving. Does that make sense? Because hydrogen would have one electron, right? Now, in reality, if we had bigger atoms, there would be many electrons off, and they would be like falling and cascading and giving off lights like Christmas time. Does that make sense? Right? So to simplify it, we do Bohr's model for the hydrogen atom. We're going to talk about one electron at a time. Now, this is how it works. If an electron were excited and it was moved out to, let's say, energy level 5, or the fifth ring of a Bohr model. Everybody put your finger right here on your sheet, on the back of your chemistry table. And let's say that when this atom cooled off, this hydrogen atom cooled off, that one electron fell all the way from energy level 5. Okay? Oops, I'm on energy level 4, aren't I? Let's go to 5. Energy level 5 is right here, right? If it fell from energy level 5 to energy level 2, do you see this drop right here? Energy level 5 to energy level 2. Then you can follow this line and you can see that 434 nanometers is the wavelength. If you look up here at the top, it says the measurement is in nanometers. So if you were right here and you're looking at an electron that fell from energy level 5 to energy level 2, then it would give off a wavelength of 434 nanometers. Okay, is everybody with me? Can you see that? And now we're going to look at this 434 down here, the bottom of our worksheet. Okay? 434 nanometers would fall in the visible light spectrum. Everybody see where I'm at? In the visible light spectrum, 434 would be right here. See, this is 4.9 times 10 to the negative 7th. But a nanometer is times 10 to the negative 9th, right? So the 434 translates to 4.34 here. Does that math make sense to you? So the 434 would be right here. What color would that be, Evan? Blue. That's right. So if an electron in a hydrogen atom were to fall from energy level 5 to energy level 2, it would give off blue light with a wavelength of 434 nanometers. Does that make sense? So it would give off blue light. Now we're going to compare that wave. Here's blue. We're going to compare that wave. Let's look at a different electron. Let's look at this electron here that falls from, let's say we heated this atom up and the electron moved out to energy level 4, and then it dropped to energy level 2. So it dropped from 4 to 2. Remember, we just did 5 to 2 last time. A drop from energy level 4 to energy level 2 will give off 486 nanometers. Now let me ask you a question. Is 486 longer or shorter than 434? It's obviously longer, everybody said. Jesus, I just said, which number is it bigger? And high school kids looked at me. All right. So 486, which will be the color of light from N4 to N2, will be a little bit longer wavelength. And then let's go down here and look at 486. 486 down here at the bottom is almost green. Does that make sense? Because 4.9 is the last edge of blue. So the light would be more green. Do you see how we can see? So let me ask you a question. Now let's talk about these waves individually. Which one of these waves, the blue wave or the green wave, has the higher frequency? The green, that's right. The blue. This is a higher frequency because the wavelength is shorter. Right? And if your wavelength is longer, then you're going to hit something less frequently. Does that make sense? Is everybody with me? I'm going to pretend you said yes. Okay, we're going to try some of this worksheet.